Hi everyone, my name is Ruichong. As you can see, I'm very excited to share our recent work with you about formation channels of magnetars. So this talk is mainly about the formation channels of magnetars from different mechanisms and the properties of magnetars from different formation channels. And also, we are going to talk about the main uncertainties from our results. So first is about magnetars. So as you must be very familiar with that. And interesting is that there are currently 31 observed magnetars in our Milky Way, but all of them are observed as single objects, which is very interesting because based on previous observations and population synthesis studies, we have know that about nearly 80% or the majority of massive stars are in binary system. Only a small fraction, like 20%, are in singles. So why all magnetars are observed in singles, which is related to the formation mechanisms. And also, like 15 magnetars has been observed with, has associated with supernova remnants, which means that the collapse supernova could be a very important mechanism to produce magnetars. And a previous study showed that merger channel could contribute to a very significant fraction to the isolated magnetars, and it's very interesting. Other channel will show that maybe the binaries could be disrupted by the supernova explosion. So what we are interested in is that based on those different formation channels and the possibilities, what are the properties of magnetars from different channels, and what are the roles of different mechanisms to amplify the magnetic field. First, let me talk about the single star evolution channel. You have a main sequence star at the first stage, and the main sequence star is massive enough to generate a neutron star. And during the collapse supernova, you can form a proto-neutron star first, and the fallback accretion can spin up the proto-neutron star's envelope, so to trigger a differential rotation. In that, to trigger the Taylor-screw dynamo to amplify the magnetic field inside the proto-neutron star. And finally, you can get a strong enough magnetic field. And for this process, you need to accrete at least a few 10⁻² or 10⁻⁻1 solar mass to trigger this kind of Taylor-screw dynamo. So, and another possibility is that you have a binary main sequence star, and maybe the separation between these two stars are very small at birth, or during the first common envelope phase, the system is failed to eject the common envelope, which will lead to the merger between these two main sequence stars. And the numerical simulation has shown that it is possible for this process to amplify the magnetic field to a very large extent, so that you can get a merger result as a main sequence star with a very strong magnetic field. And this main sequence star could evolve and finally generate a magnetar by supernova explosion. And the other possible mechanism is that you have binary system, and it has some different stage of binary evolution, and finally you got a white dwarf and the main sequence star binaries. And which we are interested in here is oxygen neon magnesium white dwarf, and trigger a common envelope phase. If the system is failed to eject the common envelope, it will lead to the merger between the oxygen neon magnesium white dwarf and the non-degenerate core of the main sequence stars. So it will cause the capture of degenerated electrons by the neon or magnesium, and cause a collapse of the white dwarf to trigger the fusion of oxygen, and finally you can get a neutron star formed by this process. And if the white dwarf has an initial larger enough magnetic field, we can expect that the neutron star could be a magnetar too. And another possibility is that during some binary interactions, you can get a very close binary system that the neutron star's progenitor, like a helium star, could be tidal spin up by its companion. And in that case, you can trigger a differential rotation inside the helium star, so that it could also amplify the magnetic field. And finally, you can if the magnetar could survive, or the binary system could survive the supernova explosion, you can expect a magnetar inside a binary system with different kind of companions. And during this process, you may not expect only co-collapse supernova to play a role, but also you can expect the electron capture or ultra-stripped supernova to generate this kind of magnetar. As you can see here, in this tidal spin-up channel, you can expect a very high angular momentum inside the core, which we expect to finally generate the magnetars. And in our previous work, we also tried to use this model to explain some different kind of transients, and which is consistent that based on the magnetar-driven model to explain these magnetars, these transients, it is possible to use this tidal spin-up mechanism to provide an energy budget. And also we can expect the AIC channel. You got white dwarf and the helium star, and if the accretion mass is large enough to make the white dwarf more massive than Chandrasekhar limitation, so the white dwarf will finally collapse to form a neutron star. And also we require that the white dwarf should have an initial large enough magnetic field so that it could generate a magnetar. And here are parameter space study based on the previous paper, and you can see that the strong magnetic field will have an influence on the mass transfer case, so the parameter space for the formation of the magnetar is a little bit different from the normal neutron star accretion. So based on all these different population or mechanism to form magnetars, we use population synthesis simulations to study this. And like this, in population synthesis, you can simulate like 1 million binaries in a single run, and you can get a different result. And the right side is the fiducial setup of our simulations. So basically, the result is like this. It's quite complicated, but we can divide it into two main different kinds. One is that the channels generate magnetars in single, and the other is to generate magnetars in a binary system. So from our fiducial model, as you can see that the majority of magnetars are in single objects in the final result. Only a small fraction, like 6% of all the magnetars could be observed in a binary system. And we also test two different parameter sets based on the recently gravitational observed constraints from population synthesis, which is a little bit larger common envelope efficiency and a little smaller kick velocity. And you can see that the change of common envelope efficiency won't have a significant change of the fractions between different channels. But if you got a smaller kick velocity, which means that the magnetar is more likely to survive through the supernova explosion, you can see the fraction of binaries of magnetars in binaries can increase like nearly 10% of all the magnetars. And also we can see that the majority of magnetar generate mechanism in here is like a co-collapse supernova explosion, which is also consistent with previous study. And another interesting is that we also studied the delay time from different channels. As you can see that the colored line represents the co-collapse supernova formation channel for both single and the binary system. And you can see this like tidal spin-up channel could also follow the trends of this co-collapse supernova, which is we think is follow the star formation history. And another like this dashed lines has a obvious delay from the star formation history. It's related to the merger channels, or like a channel with white dwarf accretion induced collapse, which means that if you expect that a magnetar found in a very old population or a very old star galaxy, maybe the magnetar comes from the merger or accretion induced collapse channel.
Got about 1 minute left.
Yes, okay. And also, if you expect a magnetar in a binary system, we also studied the different type of companions. Like you can see that the majority of companion type is a millisecond star. And also, it's possible to see the companion be a helium star or a compact objects like white dwarfs, neutron stars, or black holes. And inside these main sequence star companions, we can find that the majority of them has a relatively large mass, like larger than 2 solar mass, which we expected to be O or B type stars. And a very small fraction of this main sequence star companion has a main sequence star mass smaller than 0.7 solar mass, which could be M dwarf. And if you expect a magnetar in a binary system, we can also discuss the eccentricity after the supernova explosion. As you can see here, the most peaks around like a very small eccentricity. That is because if you expect the magnetar survive or keep bound in a binary system, the kick velocity is not that large, maybe from electron capture or ultra stripped to maintain the binary system bound. So you expect a relatively low eccentricity. And for those survived through co-collapse supernova, maybe it could have a relatively larger eccentricity. So basically, that's what we have done to use population synthesis models based on the different predictions from magnetar formation series and to study the formation channels. And the main uncertainties it comes from like, first, you need a fallback operation during the co-collapse supernova. It's model dependent. If you choose different supernova models, it may predict a different amount of accreted mass. So it will have an influence on the final fraction. And also the angular momentum transportation mechanism within the star will also have the influence of the final spin of the progenitor of magnetars, which will also have an influence on the final formation. And also other population synthesis uncertainties like common envelope efficiency or other initial mass function and the star formation rate. But also we expect that in the future, based on the observations from maybe gravitational wave side or other observations, we can constrain this parameter space and make this model more precise for magnetar studies. Thank you very much.
All right, we got time for 2 questions. You take it.
So we already know that neutron stars, like 5% of them are in binary. So what's the magnetar aspect of this exactly? How does it differ from, say, normal young neutron stars in binaries?
Yes, actually we are trying to put a constraint to our models, like we have a ratio between this magnetar and we observe the normal pulsars. We expect that the ratio is equal to 1. Yes, it's like a magnetar versus pulsar numbers is equal to 1. Yeah, the same numbers. Okay. Because there are large uncertainties here. And other questions?
Got time for one more.
Yeah, I was just curious, so based on your population synthesis models, what fraction of magnetars do you expect to exist in binaries, and is that number consistent with the fraction of active repeating FRBs?
Yes, as you can see here, the largest fraction of binaries in our simulation is right now relative to a very small peak, is like 10%. And as shown in previous talk, like repeaters is nearly 8-something%, right? So maybe it's related to the active repeaters. And also you need to consider that all the magnetars inside our Milky Way right now is in single stars, which means that the single magnetar formation channel, which is the majority. Yeah.
So what are the uncertainties on those fractions that you quote based on like the uncertainties from population synthesis models or
Yes, there are basically 2 different kinds. One is the uncertainties from the models from the formation mechanism of magnetars. Like here, you require the fallback operation. It is relatively based on the supernova model, which is still under debate, right? And others from population synthesis is like some certain physical process. The parameters is not well constrained, but we can get relatively reasonable parameters from the observational side, from like a gravitational wave source.
So are these uncertainties like percent level or 10% level, like when you look at those fractions that you mentioned?
Yes, that's a good point. We are also trying to do more different parameter tests so we can get the relatively